In this module, I am going to discuss about VSEPR theory in the form of MCQ. Question number 1. When applying VSEPR theory to predict molecular shape, which of the following do we not need to take into account? Option A. Valence electrons occupying sigma bonding orbitals. Option B. Valence electrons occupying pi bonding orbitals. Option C. Valence electrons occupying non-bonding orbitals. The VSEPR theory primarily consider the arrangement of valence electrons in sigma bonding orbitals and non-bonding orbitals to determine the molecular geometry and shape. Pi bonding orbitals are typically associated with multiple bonds such as double or triple bonds and don't have a significant influence on the molecular geometry as predicted by VSEPR theory. So, when we apply VSEPR theory to predict the molecular shape, we do not need to take into account the valence electrons occupying pi bonding orbitals. Hence, the correct answer, option B, valence electrons occupying pi bonding orbitals. Question number 2. The number of lone pairs are identical in the pairs. Option A, xenon tetrafluoride and chlorine trifluoride. Option B, xenon tetraoxide and tetraiodine tetrachloride anion. Option C, xenon difluoride oxide and tetraiodine tetrachloride anion. Option D, xenon tetraoxide and chlorine trifluoride. In xenon tetrafluoride, xenon is the central atom and it has 8 valence electrons. Xenon forms covalent bonds with 4 fluorine atoms. Each fluorine atom contributes 1 electron to the bond and xenon shares one of its valence electrons in each bond. This results in the formation of 4 sigma bonds between xenon and fluorine. In addition to the sigma bonds, xenon also has 2 lone pairs of electrons. The 2 lone pairs of electrons not involved in bonding, these lone pairs are located above and below the square formed by the fluorine atoms. In chlorine trifluoride, chlorine is the central atom and it has 7 valence electrons. Chlorine forms covalent bonds with 3 fluorine atoms. Each fluorine atom contributes 1 electron to the bond and chlorine shares one of its valence electrons in each bond. This results in the formation of 3 sigma bonds between chlorine and fluorine. In addition to the sigma bonds, chlorine has 2 lone pairs of electrons which are not involved in bonding. These lone pairs are located above and below the plane formed by the 3 fluorine atoms. Hence, the number of lone pairs are identical in the given 4 options. The correct answer is option A, xenon tetrafluoride and chlorine trifluoride. Question number 3. The structure of xenon dioxide difluoride based on VSEPR theory is best described as option A, a square planar structure with the fluorines trans to each other. Option B, a perfect tetrahedral arrangement of substituents around xenon. Option C, seesaw structure with the central atom xenon is covalently bonded with two fluorine atoms, bond angle close to 120 degrees. Option D, seesaw structure with the central xenon atom is covalently bonded with two oxygen atoms, bond angle close to 120 degrees. In xenon dioxide difluoride, the central atom is xenon. It has 8 valence electrons. The surrounding atoms include 2 monovalent fluorine atoms and 2 divalent oxygen atoms. By adding the valence electrons of xenon and the monovalent fluorine atoms and then dividing the sum by 2, we obtain 5 electron pairs. The final number 5 indicates sp3d hybridization. In xenon dioxide difluoride, there are 5 sp3d hybrid orbitals. These orbitals consist of 4 bond pair and 1 lone pair around the central xenon atom. Xenon dioxide difluoride molecular geometry is originally said to be trigonal bipyramidal, but due to the presence of lone pairs on equatorial positions, the actual shape will be seesawed. The repulsion between the bond pair and lone pair of electrons will be more. In xenon dioxide difluoride, fluorine will be axial atoms and oxygen will be equatorial atoms. As for the angle, the bond angle for xenon atom covalently bonded to 2 oxygen atom is close to 120 degrees and bond angle for xenon atom covalently bonded to 2 fluorine atom is close to 180 degrees. Hence, the correct answer option D, seesaw structure with xenon atom covalently bonded to 2 oxygen atom, the bond angle close to 120 degrees. Question number 4. Select the incorrect statement from the following statements. Option A, the geometry of water molecule is bent. Option B, the shape of nitrite ion is planar. Option C, the geometry of sulfur tetrafluoride is trigonal bipyramidal. Option D, the shape of ozone molecule is trigonal planar. We have to follow few steps to predict the shape of the molecule. At first, we have to select the least electronegative atom as the central atom. Secondly, we have to count the valential electrons of the central atom. We have to find out the type of hybridization based on the number of orbitals participating in bonding. Shape of the molecule to be assigned based on the hybridization. We have to count the number of bond pairs and lone pairs in the molecule. The idea of lone pair gives the correct shape of the molecule. In water molecule, the central atom is oxygen and it is surrounded by 2 hydrogen atoms. In the case of water, the central atom oxygen contributes 6 electrons to the sp3 hybridization and the 2 hydrogen atom contributed a total of 2 electrons. Hence, the total number of electrons available for bonding is 8. To know the total number of electron pairs, we have to divide 8 by 2. The total number of electron pair is 4, out of which there are 2 bonding pair and 2 lone pairs. Water molecule formed by sp3 hybridization. The expected geometry of the molecule is tetrahedral. The lone pair of electrons exert a stronger repulsive force on the other electrons compared to the repulsion between the 2 hydrogen atoms. To minimize the repulsion between these electron pairs, the molecule adopts a bent, V-shaped geometry. This results in an angle of approximately 104.5 degrees between the 2 hydrogen-oxygen-hydrogen bonds, creating the characteristic bent structure of a water molecule. In nitrite ion, the central atom is nitrogen. It is surrounded by 2 oxygen atoms. In the case of nitrite ion, the central atom, nitrogen, contributes 5 electrons to the sp2 hybridization. The 2 oxygen atom contributes a total of 12 electrons. When forming the nitrite ion, 1 extra electron is added, giving us a total of 18 valence electrons to distribute among the 3 atoms. The nitrogen atom is placed at the center and it is bonded to 1 oxygen atom through a double bond and to the other oxygen atom through a single bond. The remaining electrons are arranged as lone pairs on both oxygen atoms. To minimize electron repulsion and to achieve a stable structure, the electrons are distributed in a way that results in a bent geometry for the nitrite ion. The repulsion between the lone pairs on the oxygen atoms and the shared electrons in the bonds causes the bond angle to be less than 120 degrees, resulting in a bent shape. In sulfur tetrafluoride, the central atom is sulfur and it is surrounded by 4 fluorine atoms. In the case of sulfur tetrafluoride, the central atom sulfur contributes 6 electrons to the hybridization and the 4 fluorine atoms contribute a total of 4 electrons. Hence, the total number of electrons available for bonding is 10. To find the total number of electron pairs, we have to divide the total number of electrons by 2 and we get 5. Out of 5 electron pairs, there are 4 bonding pair electrons and 1 lone pair electrons. Sulfur tetrafluoride molecule is formed by sp3d hybridization. The expected geometry for the sulfur tetrafluoride molecule is trigonal bipyramidal. But the arrangement of bond pair and lone pair electrons results in the seesaw shape with a bond angle of approximately 90 degrees between the fluorine atoms and the lone pair. The seesaw geometry minimizes electron repulsion and provides the most stable arrangement for the electrons in the sulfur tetrafluoride molecule. Ozone consists of 3 oxygen atoms and each oxygen atom contributes 6 valence electrons to the molecule. This gives a total of 18 valence electrons. To achieve a stable molecular structure with minimum repulsion, one oxygen atom forms a double bond with the central oxygen atom. This double bond involves the sharing of 4 electrons. The remaining 2 oxygen atoms each form a single bond with the central oxygen atom. Each single bond involves the sharing of 2 electrons. This distribution results in a bent or V-shaped structure for the ozone molecule. The bond angles between the oxygen and oxygen atoms are approximately 116 degrees. The repulsion between the lone pairs of electrons on the oxygen atom and the shared electron pairs in the bonds causes this bent geometry, as it minimizes the repulsive forces between electrons and maximizes the stability of the molecule. Water molecule adopts bent geometry shape. Nitrite ion has bent shaped geometry. Sulfur tetrafluoride has seesaw geometry. The shape of ozone molecule is bent. So the correct answer option 4, B, C and D only. Question number 5. Calculate the percentage of S character in the lone pair electrons of NH3, where the percentage S character of bond pair is 22% in each nitrogen-hydrogen bond. Option A 60%, option B 25%, option C 44%, option D 34%. The number of nitrogen-hydrogen bond present in ammonia molecule is 3. So the percentage of one bond pair showing S character is 22%. The 3 nitrogen-hydrogen bonds showing S character is calculated by multiplying 22% with 3. This gives 66%. The percentage of S character in the lone pair of ammonia molecule is obtained by subtracting 66% from 100% and we obtain 34%. Therefore, the percentage of S character in the lone pair of ammonia molecule is 34%. Hence, the correct answer option D 34%.